Bismillahirrahmanirrahim. So today in this video we will try to learn about triaxial test and we will cover all the details regarding this test. So first of all, we need to know that why we perform triaxial test. So triaxial test is used to find out the shear strength parameters of the soil. So we can determine the cohesion and angle of internal friction using triaxial test. We can also obtain the effective shear strength parameters, cohesion and angle of internal friction from triaxial test. In addition to that, we can also determine the modulus of elasticity from triaxial test. So these are the basic purposes of triaxial test. Now the next question arises that we can determine the shear strength parameters from direct shear test. So why we need to perform triaxial test? So the reason is direct shear test has certain limitations because of which we need to perform the triaxial test. So let's discuss those limitations of direct shear test, then you will get the idea that why we need to perform triaxial test. So limitations of direct shear test. DST stands for direct shear test. So in direct shear test, one of the limitation is predetermined failure plane. It means we already know the failure plane direction, like soil sample will always fail in this manner. So it means we already know the failure plane of the soil sample in direct shear test. That is the limitation of DST basically, because soil sample generally does not follow this failure direction. That is why it is considered as one of the limitation of the direct shear test. So this limitation will be compensated in triaxial test. And then the next limitation is no pore water pressure measurements. No pore water pressure measurements. In direct shear test, you cannot measure the pore water pressure. So that is why we need to perform the triaxial test. In triaxial test, we can measure the pore water pressure as well. And the third and the most important limitation is field simulation. Field simulation. In direct shear test, we cannot simulate the field conditions in a very accurate manner. This means in field, if we extract the soil sample from, let's say, 10 feet depth, this is a ground level, and if we extract a soil sample from 10 feet depth, so it means this soil sample is surrounded by certain stresses. But in direct shear test, we try to develop the failure envelope by applying predetermined normal stress like 50, 100 and 200, sometimes 25, 50 and 100 kPa normal stress. But this is not the actual field conditions. So in triaxial test, we can simulate the exact field conditions in triaxial test. For example, if we have extracted a soil sample from 10 feet depth and the average unit weight of this soil is 17 kilonewton per meter cube, then it means this sample is surrounded by 170 gamma into H. If it is like 10 meter, let's say 10 meter, sorry, it is 10 meter, just to be the understanding the convenience of having the same units. So that is why I just changed it to 10 meter. So it means the normal stress at that point is 170 kPa. So we can apply 170 kPa normal stress in the triaxial test. So this is how we can simulate the field conditions in triaxial test. So these are the limitations due to which we need to perform the triaxial test for more accurate assessment of shear strength parameters. So let's move on towards the description of triaxial test. So stages. Triaxial test is performed in 3 stages. First stage is saturation. So when we obtain the soil sample from the field and we want to measure the shear strength parameters using the Triaxial test, the first step is to saturate the soil sample. Second stage is the consolidation, but it is related to the drainage conditions, whether we will apply the consolidation or not. And third stage is the shearing, because soil fails in shear, so that is why we need to have the shearing process in the third stage. So soil sample is, so we can determine the shear strength parameters using Triaxial test after passing the soil sample through these stages. Saturation is required because when the soil sample is fully saturated, it means it is in its worst condition. So we always obtain, or we always design on the worst case scenario, so that is why we fully saturate the soil samples. Then consolidation, this is a natural phenomena which happens when the clay or cohesive soil is fully saturated. Then with the passage of time there will be seepage, there will be some water that will dissipate from the soil sample, and due to the dissipation of water under the certain loading, there will be some settlement. That process is known as the consolidation. Then we apply the then we simulate the field condition, and under field conditions we try to fill the soil sample in compression. That is called basically shearing. Now the next step is to understand which type of Triaxial test we need to perform. So types of TST, Triaxial test. So there are 3 types of Triaxial test. One is UU, second is CU, and third one is CD. So the first type of test is UU. UU stands for unconsolidated undrained test. Unconsolidated undrained test. Unconsolidated undrained test. Similarly, CU stands for consolidated undrained test and CD stands for consolidated drain test. So what does it mean? For every Triaxial test, you need to look at the stages of the Triaxial test. For example, unconsolidated. It means if you are going to perform UU test, then you will first saturate the soil sample, then you will see what is the first alphabet of the type of test. Let's say U. U is related to the second stage of the Triaxial test. Here you can see unconsolidated. It means if you are performing UU test, after saturation you will not perform the consolidation process. So first letter of the type of the test is related to the second stage, whether you need to perform the consolidation or not. So it means in UU test you will not perform consolidation. That is why it is unconsolidated. Now, what does it mean by the second letter of the type of the test? That is undrained. It means firstly you will saturate your soil sample, then you will not perform consolidation in UU test. So the next step is to shear the soil sample under the compression, and during the shearing you will have the undrained conditions. You will not allow water to dissipate while shearing the soil samples. So this letter, second letter of the type of the test, is related to the third stage. So this is how you perform the UU Triaxial test. Now let's understand what is meant by CU, consolidated undrained test. So saturation is the must process for every type of the test. You will perform saturation, then you will see what does it mean by the C consolidated. It means in the second step, consolidation will be performed if you are going to perform CU test. So when the consolidation stage is completed, then you move on towards the sharing, and during sharing you will keep the condition undrained because it is undrained, consolidated undrained. Then the next test is consolidated drained. For this test again you will perform saturation, then C, consolidation, means you will perform consolidation, then drain. During sharing your condition will be drained. So this is how we understand the type of test and the meaning of these types of triaxial tests. Now move on towards the next step, sample preparation, and then we will move on towards the saturation process, how we saturate the soil sample in triaxial test. So sampling or sample preparation we have already discussed regarding this. Sample preparation for triaxial test. So there are 1 to 2 steps to prepare the soil sample. One is, if you have undisturbed sample, you just need to cut the samples according to the dimensions of the mold of the triaxial test. So if you have undisturbed sample, you just need to trim the soil sample according to the dimensions of the mold. Then the next step is to prepare the soil sample, to prepare the remold soil sample, remolded soil sample, remolded soil sample. So how you prepare the remolded soil sample? For remolded soil sample, you must have the density of the soil, density. If you have gamma bulk or if you have gamma dry, let's say you have gamma dry for a soil sample, let's say it is 1.7 gram per centimeter cube. And then you must have the natural moisture content, NMC. NMC, let's say, is 10%. So you must have these two values if you want to remold your soil sample. So these values can be obtained in a different ways. I will be explaining those ways as well. So for the time being, I'll be telling you that how to remold the soil sample. So for remolding the soil sample, you need dry density or bulk density, and then the moisture content of the soil sample from where you have extracted the soil. Okay, let's say you have these two parameters and you want to remold your soil sample. Then how to remold the soil sample? Remember, for remolding the soil sample, you must have the mass of soil. Mass of soil to be placed in mold of the triaxial test, and then mass of water. So these are the two outputs of the remolded soil sample. You must compute from these quantities, mass of the water. So how we obtain these quantities? If we are given the dry density, so as we know that density is equals to mass per unit volume, So if you have mass and you have the volume of the mold, then you can, if you have the density and volume of the mold, you can find out the mass of soil that will be placed in the mold. So we will obtain this using this formula. Gamma dry, it will most probably be weight into volume. So you will multiply 1.7 into volume. So volume of the mold can be computed by the formula V is equals to pi by 4 d square into h. So if your soil sample is of spherical or circular or cylindrical sample, then you will use this formula to determine the volume of the mold. Like d is the diameter of the mold and h is the height of the mold. So usually we have the diameter like 70 mm dia, and 140 mm height. So using these dimensions, you can find out the volume of the mold. You will simply multiply volume with the dry density and you will obtain weight of dry mass of soil that is required to perform the test. Let's assume you find out the weight of the soil sample that comes out to be, let's say, 100 gram weight of soil sample. And if the moisture content is 10%, so 10% of water will be 10 gram. So basically the density of water is 1 gram per centimeter cube. So you can take the you can take the unit of water as gram as well. So 10 gram, because this is 10% of this dry mass of the soil. So this is how you obtain weight of soil sample and weight of water. You mix both these quantities and then you place these in a mold in the layers and compact the soil sample so that these soil must fill the mold. This is how you remold the soil sample. Now in the next stage, if you have prepared the soil sample, you will assemble the apparatus of the triaxial test, and then you will, in the first step, in the first stage of the triaxial test, you need to perform the saturation. So let's understand how we saturate the soil sample in triaxial test. So for the saturation stage, let's say this is the soil sample and this is the triaxial cell chamber. Now we want to saturate this soil sample, fully saturate the soil sample. So in the first step, we apply the cell pressure. Cell pressure is basically the confining pressure. Confining pressure. Because in the field, soil is confined from the stresses all around. So in the first step, we apply the cell pressure. Cell pressure. So as we will move from the lower dimension to the higher dimensions, or lower values to the higher values. So that is why initially we'll apply 20 kPa of cell pressure, 20 kPa of cell pressure, and this cell pressure will produce the pore water pressure in the soil sample. So let's say pore water pressure produced is 5 kPa when we apply the 20 kPa cell pressure. So at this stage, the saturation can be found out by 5 pore water pressure divided by cell pressure. So we can find out the saturation. It means at this stage there is 40% saturation in the soil sample. I think it's 40%. This is called Skempton's coefficient, beta. When this is equal to 100% or 1, then it means the soil sample is fully saturated. Now at this stage we have 40% saturation. So in order to facilitate the saturation process, we apply the back pressure. Back pressure is the direct induction of soil sample into the direct induction of water into the soil sample. So this is through any cell we apply the back pressure. So in the first step we will apply 15 kPa of back pressure. We will always keep this value lower from the cell pressure. If we will increase this value from the cell pressure, because back pressure will be a reaction pressure to the confining stress. So if it is more than the confining stress, then the soil sample will burst up. So that is why we'll keep it as 15 kPa. Then we will observe that how much pore water pressure is produced. So now again, if the pore water pressure from 5 kPa increases from 5 kPa to 10 kPa, then we will again measure the pore water pressure, and you can see the pore water pressure is now 10/20 into 100. So it means at this stage there is 50% saturation. Now again we will increase the confining pressure in the next stage, and we will observe the pore water pressure, and then we will check that how much saturation has been occurred till this point. So we'll keep this process running until or unless we obtain the 95 to 100% saturation. So this is how we saturate our soil sample. This is how the saturation process is completed. In the next stage, if we are performing UU test, then we don't need to perform the consolidation, and we'll directly share the soil sample. I will elaborate that how we will share the soil sample. And if we are performing CU, consolidated undrained test, then we will consolidate the soil sample. How we will consolidate the soil sample? Now, let's say we are performing CU test and the first stage of saturation has been completed. In the next step, we need to consolidate the soil sample. So before consolidating the sample, we need to simulate the field stresses. Simulate field stresses. So how we simulate the field stresses, as I explained earlier, if we have extracted the soil sample from 10 meter depth, and the average unit weight of soil sample is 17 kilonewton per meter cube, then the stress will be 170 kPa at this stage. So we assume that 170 kPa is applied in the field to this soil sample in all around direction. Okay, so now we'll apply 170 kPa stress, that will be called confining stress. At this stage, sigma 3 is equals to sigma 1. So that is why we call it as sigma 3. So we'll apply 170 kPa stress through the air pressure. In triaxial test, we apply this confining stress using the air pressure. Air pressure can be applied using the air compressors. So using air compressors, we'll apply 170 kPa. 170 kPa will be obtained from the field conditions. So this is how we simulate the field stresses. Now we will allow this soil sample to dissipate the water just to have the consolidation, just to proceed with the consolidation process. Then what will happen under this confining stress, under this field stress, water will start dissipating, and there will be some burettes through which you will note down the movement of the water. So when the water level is constant, after some time, it may take 60 minutes, it may take 2 hours. So you need to observe that when the water level in the burette is constant, it means that consolidation process is completed in the soil sample, and there will not be any drainage through the water, through the soil sample after this time. So when the consolidation is completed, in the next step, now we need to share the soil sample. Sharing the soil sample. In order to share the soil sample, just like UCS test, we will apply the compression. Now we'll try to fill the soil sample. We'll apply the stress using a strain controlled condition. So we'll adjust a shear rate. Shear rate is calculated based on the soil type. We will have another detailed video regarding the shear rate, that how we determine the shear rate. So let's say we have the shear rate for the clay soil sample is 0.5 mm per minute. So at this rate, stress will be applied, and we'll observe that when the soil sample will be failed. And this additional stress is called delta sigma d, sometimes deviatoric stress. This is known as deviatoric stress or deviatoric stress. Sometimes deviatoric or deviatoric stress. Okay, in the next step, how we will terminate this test? So there are 2 to 3 criteria which are used for the decision regarding the termination of the test. So what are those criteria? First criteria is when the strain reaches up to 20%, then you will stop the test. For example, if the soil sample is having 140 mm height, so if we apply the 0.5 mm per minute shear rate, when the displacement in the soil sample is 20% of 140 mm, that is equals to 28 mm. If the displacement in the soil sample has been reached up to 28 mm, then we will stop the test. Next criteria is strain stress. So while shearing, there will be increase in stress, and correspondingly there will be an increase in the strain. So if stress decreases after some point before the 20% strain criteria reached, then we will stop the test and we'll just obtain some reading after the peak value, and we will terminate the test. So these are the criteria which are used to decide regarding the termination of the test. Well, this is how the 3 stages of Triaxial test are completed. Now let's move on towards the calculation, how we calculate the shear strength parameters. Let's say we are doing a CU test, and in the first column we'll note down the time, we will note down the displacement, we will note down the load. Remember, if you are performing a test in laboratory, you will obtain displacement dial readings. You need to multiply that reading with the least count of the dial gauge in order to obtain the value in the units. For example, in our lab, the rate least count for the dial gauge is 0.01. It means you will multiply displacement dial reading with the 0.01 in order to obtain the value in mm. Let's say this is for example. Similarly, you will have proving ring reading. So you will multiply that proving ring reading with the least count of the dial gauge in order to obtain the load value in a unit. It can be in kilonewton in cat, it can be in pounds, and it can be in kg. So let's say I'll directly writing the value in load in kilonewton. You will compute that value, and then you obtain the corrected area that is equals to original area over 1 minus strain. Okay, so in order to compute the corrected area, you need to put the strain over here. Strain is basically delta L over L. If you want to convert it into percentage, you will multiply it by 100. So delta L is basically displacement. L is the total length of the sample, that was 140 mm. So you will divide these two quantities in order to obtain the strain, and in the next step you will obtain the corrected area, that will be original area over 1 minus strain. So this is necessary because when you shear the soil sample in the initial stage, if the soil sample is like that, so during shearing, soil sample will fail in, there will be some shear planes. So here you can see the cross-sectional area is different, cross-sectional area is different, cross-sectional area is different. So that is why we need to apply the corrected area, because, and it is related to the strain. And if you observe from this formula, corrected area will always be greater than the original area, because when anything will be subtracted from the 1, the value will be in 0 point something, and if we divide 0 point something from any value, it will enhance the value from this term. So that is why corrected area will always be greater than the original area. So this is the concept of obtaining the corrected area. In the next stage, you will obtain the stress. This is basically deviatoric stress at that stage. So deviatoric stress is load per unit corrected area. So you will obtain this value. Now you have delta sigma D, and you will have the pore water pressure over here. Let me redraw this table again. Time, displacement in mm, load in kilonewton, then you must have strain, delta L over L, then you have corrected area, then you need to determine the pore water pressure. You can obtain these values from the dial gauges. You will try to record these values with the time. So you will have the pore water pressure. Now in the next stage, you need to determine the sigma 3, sigma 1, etc. So deviatoric stress, you will obtain deviatoric stress, this load divided by corrected area, and you will obtain the deviatoric stress. Now, as you know that sigma 1 is equals to sigma 3 plus delta sigma D, so you will obtain sigma 1 like sigma 3 is 170 kPa. As I told you, the confining stress, the field simulation stress will be 170, plus you will add on deviatoric stress, and you will end up obtaining sigma 1, the maximum sigma 1, the maximum value of sigma 1. Let's say it is 330 kPa, and you have sigma 3 170 kPa. If we are not considering the pore water pressure, and you have these two parameters, sigma 3 and sigma 1, these are total stress parameter. Now in the next step, you again perform the next trial. So in the first trial, you have sigma 1, let's say 330 kPa, and sigma 3, let's say 170 kPa. Now in the next trial, you will double the value of sigma 3, that will be 2 into 170 kPa, and then you will observe what is the value of sigma 1. So let's say it is 700 kPa sigma 1 value. You perform these two trials, and you obtain sigma 1 and sigma 3 from these two trials. Then you have to plot the Mohr circle. So here you will plot the sigma. For the first trial, let's say it is 170 kPa somewhere here, and for the first trial, sigma 1 is somewhere here, that is 330 kPa. You will obtain the center of this circle by adding these two parameters, 170 plus 330 divided by 2. You will obtain the center of the circle. You will draw a Mohr circle for the trial 1. Similarly, for the trial 2, you will plot the Mohr circle like using sigma 3 and sigma 1 value. You will obtain these two circles. Now you will draw a tangent that is passing from these two circles, and the y-intercept will be cohesion, and this will be the phi. So this is how you obtain the total stress or total shear strength parameters. If you want to determine the effective strength parameters, what you will do is you will subtract the pore water pressure from sigma 1 and sigma 3 values. Then you will obtain sigma 1 prime and sigma 3 prime. Similarly, you will draw Mohr circle for both the trials, and you will obtain the effective shear strength parameters C prime and phi prime. So this is how we perform the triaxial test and we obtain the total shear strength parameters and effective shear strength parameters using triaxial test. So I hope you like the video. If you like the video, don't forget to subscribe, share. Thank you. We'll meet you in the next video. Thank you.